Oak Ridge personnel and Tormod Rista from Norway. And then I'll say, and most of what I'll say will be about longitudinal polarization analysis, because that's the sort of thing that is most widely used. Then I'll talk very little about something called spherical neutron polarimetry. In the longitudinal polarization analysis, what you'll see is that the polarization state of the neutron is defined throughout the entire experiment by a magnetic field. In spherical neutron polarimetry, the idea is that the sample is not in a magnetic field, and so you can bring the direction of polarization of the neutron into the sample at any direction relative to the, let's say, the crystal axes of the crystallographic axes of the sample. And by the same token, you can also analyze the direction of polarization of the scattered beam. And then to sort of tell you what uses have been made of polarization analysis and polarized neutrons, I'll sort of salt the talk all the way through with some references to actual experiments that have been done with polarized neutron diffraction, polarized neutron small angle scattering, reflectometry, and one that I forgot to put on the slide, inelastic scattering. So let's first talk about the neutron spin and its magnetic moment. So the neutron, of course, is a fermion. It has a spin of 1/2. And because it has a spin of 1/2, there are two states that can be eigenstates of the so-called SZ operator, this one over here, which is the operator which looks at the state of the neutron spin relative to some quantization axis, which we call Z. Because there are two states for a spin-half particle, you can represent any combination of those states as a vector in two-dimensional space, which is, of course, why these operators that represent the spin operators can be written as two-dimensional matrices. So these are the standard matrices that you will see as the spin operators in any quantum mechanics course that you would do as a graduate student. You will see here the SX operator, the SY operator, and then this SZ operator. Normally, what we do is, because we're too lazy to write this h bar over 2 in front here, this thing, of course, is an operator which gives the spin angular momentum of a particle as the eigenvalue. Normally what we do is to take out this factor of 2 over h bar, multiply it through here so that it cancels out, and produce this thing called the Pauli spin operator, which then has eigenvalues of plus or minus 1. You can see that, for example, for SZ, so if we look at SZ, for example, and you just take SZ times a vector which represents one state of the neutron, that's going to be just h bar over 2, 1, 0, 0, minus 1 times 1, 0, which is just going to be h bar over 2 times 1, 0. In other words, this vector, eigenvector here is an eigenvector of this spin operator SZ with an eigenvalue which is just h bar over 2. If you were to do the same thing, but use instead of this vector here, the vector 0, 1, then what you would get at the end is just a minus h bar over 2 times 0, 1. In other words, this vector here is also an eigenvector of this spin operator with an eigenvalue of minus h bar over 2. And if we were to use the Pauli matrices, the h bar over 2 would go out, and we would be left with eigenvalues that are plus or minus 1. It's quite easy to convince yourself that these states are not eigenstates of the Sx or Sy operators. All you have to do is to write down, for example, something like Sy times the 1, 0 vector, and you'll get 0 minus I 0 times 1, 0. And this will give you something like H cross over times over 2 times 0 I. In other words, this thing is not equal to an eigenvector of the Sy operator. So the state of the neutron is an eigenvector of the Sz operator, but not an eigenvector of the Sx and Sy operator. So now let's see if we can do this. We have to go through some manipulation. Quantum mechanics that you will have probably learned in your graduate quantum mechanics course. The neutron also has a magnetic moment. For a particle which is charged, like the electron, you know that if you imagine a charged particle spinning, that it will have a magnetic moment. After all, it has a circulating current, and the circulating current will cause a magnetic field which will look like it comes from a magnetic moment. The neutron, of course, doesn't have a charge, so it's not like the electron where you would automatically say, okay, it's got a spin a half, it's charged, it must have a magnetic moment. The neutron has a magnetic moment just like the electron, but not for the same reason. And in fact, the fact that the neutron was found to have a magnetic moment as well as a spin of a half was kind of a smoking gun, which indicated to people that it couldn't be an elementary particle. And in fact, the neutron's magnetic moment comes from the magnetic moments of the quarks that go to make it up. The neutron's magnetic moment is a lot smaller than the sort of typical magnetic moments that you think about with an electron. Here you can see the magnetic moment, which is some number times this thing here, which is called the nuclear magneton. And the nuclear magneton is EH cross over 2 times the mass of the proton. If you were thinking about a Bohr magneton, which would be the typical magnitude of a magnetic moment for an electron, you would replace this mass of the proton down here with the mass of an electron, so you'd get something that was about 1,000 times bigger. So this magnetic moment of the neutron is about 3 orders of magnitude smaller than the typical values of the Bohr magneton. You'll notice, however, that this minus sign in here, and that means that the magnetic moment is antiparallel to the spin of the neutron, which is the same as for an electron, but for different reasons, as I pointed out earlier. So those are the fundamental quantum mechanics of a neutron and its spin and its magnetic moment. Of course, you can write the neutron spin wave function as a superposition of these two states that I wrote on the blackboard as vectors, the 1, 0 and the 0, 1 vectors. Those two states tend to get called the up and the down states. In a sense, you can say that the 1, 0 state, the vector 1, 0, is a state with the spin parallel to the quantization direction, and the state 0, 1 is a state which is antiparallel. Remember, the eigenvalues have opposite signs. I showed you that they were plus h bar over 2 for the spin angular momentum for one state and minus h bar over 2 for the other state. So those states are usually called up and down, and you'll hear people refer to them as up and down, and often people will write them in this way as a state where the spin is up. and this one is a state where the spin is down, meaning that this one has the positive eigenvalue and this one has the negative eigenvalue. And any wave function or spin-dependent part of the wave function of a neutron can be written as a linear combination of those two things. Now, if you want to find out what the polarization of an individual neutron is, what you have to do is to take the expectation value of, let's say, the Pauli matrix along x with this wave function chi, do the usual thing and work out what the expectation value is, and that will give you the polarization along the x component of the polarization of this of the neutron. Now, it turns out that's not a very useful quantity, but let's just, for the moment, let's just make sure that we know how to do it, and we'll come back to why it isn't a very useful quantity in a second. But so if you were to try to work out what this px is, you would try to work out px as a expectation value of the Pauli X matrix, then of course what you would have is, since chi, as I said, is A times up plus B times down, in my vector notation this would be equivalent to A times the 1, 0 plus B times 0, 1, or equivalently AB. And so in order to do this thing, all I would need to do is to write the x component of the polarization as A comma B as a row vector times the operator which corresponds to the Pauli X state, and then the complex conjugate of this state vector, and this will give you A times B star plus B times A star, which is just twice the real part of A star times B, which is the value that was on the view graph. So let's see if we can again go back to this thing. Y component, and you can do the same thing for the Z component. And all of those things you can define for a single neutron. It's tempting, of course, to think about these px and py here as if they're the components of a vector. To say that, okay, I found the expectation value of the sigma x operator, and that's px, and now I'm going to think of the polarization as a vector in 3 space where I have 3 components, px, py, and pz. That turns out not to be a useful thing to do. And the reason it's not a useful thing to do is that you can't simultaneously measure all 3 of these for a single neutron. For a single neutron, remember, it can be in an eigenstate of, each one of these 2 states is an eigenstate of pz, but it's not an eigenstate, eigenstate of sigma z, but it's not an eigenstate of sigma x or sigma y. So for a single neutron, this is what you're tempted to do, which is to say that this is a classical vector, doesn't work. But you can define it for a neutron beam because you can measure it. So what you can do with a neutron beam is because you've got a statistical ensemble of many neutrons, is you can actually measure the various components of the polarization for the neutron beam. And that will be the average, that will be the mean value of each of these quantities averaged over the beam. And you can see that the polarization along the z direction is just this quantity a squared minus b squared. You know from your quantum mechanics that the a squared is just the probability of measuring this state when you make a measurement. And b squared is the probability of measuring this state when you make a measurement. So if you take a beam and you measure the number of neutrons in this state, that will be proportional to a squared. You measure the number of neutrons in this down state, that's proportional to b squared. Obviously what you have to do is to subtract the number of neutrons in the up state, in the down state from the number of neutrons in the up state, and then to normalize the whole thing, you divide by the sum of the number of neutrons that you counted in the beam. And that's the definition of the polarization of the neutron beam. So these three components of the beam polarization, notice that not the polarization of a single neutron, but the beam polarization, you can think of in terms of a classical vector. And it's often very useful to do this because you can get an image in your head as to what the polarization of the beam is doing in various situations. Experimentally, all of the devices that we have available to measure a polarized beam will always do something like either transmit or reflect one of the two spin states preferentially. And that spin state, of course, is defined with respect to the z direction, which means with respect to a magnetic field. So experimentally, always what we'll be doing when we measure a beam polarization is measuring a number of neutrons whose spins are parallel to the magnetic field, and a number of neutrons whose spins are anti-parallel to the neutron field, the magnetic field. In other words, the number that are up and the number that are down. And the polarization then, along this direction of the magnetic field, which is the quantization direction that we've defined, the polarization of the beam is defined as the number we measure with transmitted with upspin minus the number transmitted with downspin divided by the sum to normalize it. And you can see that this number is a number between +1 and -1. And so the polarization of a neutron beam is always a number between +1 and -1. If the number is 1, then what that says is that all of the spins are aligned in one direction with respect to the magnetic field. In other words, all of the magnetic moments are anti-aligned to the magnetic field. And if the polarization is -1, then all of the spins are anti-aligned with respect to the magnetic field. You'll never, by the way, see a value which is 1 experimentally. The best you'll see is 99 and a few %. But in principle, you can go all the way between -1 and 1. So now we know what a polarized neutron beam is. It's a beam which is predominantly composed of one of the neutron spin states. And the sort of experiment that we're going to do is an experiment where we scatter these polarized neutrons from a sample and analyze what the polarization state is. So the experiment will consist, if it's complete, of measuring 4 different cross-sections. And I've given them here as the elastic cross-sections, in other words, d sigma, d omega, but I could equally well have written these as the full inelastic scattering cross-section that you've been introduced to in previous lectures. The point is that here I've appended to these scattering cross-sections these plus plus, minus minus, plus minus, and minus plus symbols. And what these indicate is that I'm measuring, in this particular case, in this first case, I have neutrons, a neutron beam, which is in the up state. In other words, it has a polarization of 1, it's plus. And I'm going to analyze the neutrons that are scattered from the sample. And those are also going to be in the up state with a +1 polarization. So this term here is going to measure for me, if I take a neutron with a spin up and it scatters from a sample, what's the probability that it will have a spin up? The second term is going to be down to down. The third term is going to be up to down, and the fourth one is going to be down to up. that's a complete set of terms, and we'll come back to seeing why they might well be different. Now, these first two here, the state of the neutron doesn't change when it's scattered by the sample. In these last two, the state of the neutron does change. It goes from up to down here, and from down to up here. These last two are referred to as spin flip cross sections, because the neutron spin is flipped during the scattering process. By extension, the first two are referred to as non-spin flip scattering, because the state of the neutron doesn't change during the scattering process. So that's some nomenclature that you probably should try to remember. Okay, now let's talk a little bit about the scattering of neutrons from a system and what may happen to the neutron spin state. Now, if you learn anything from Professor Braham's lectures, you should remember that this scattering cross-section here, d sigma d omega, has this magic factor of the mass of the neutron over 2 pi h bar squared in front, and then is just a square of a matrix element. I hope they got that, Colin. So Colin, Professor Braham is in the room with me, so he's confirming you should know that. What this means is that you've taken a neutron with a wave vector k, defined as 2 pi over its wavelength, and a direction of, it's a vector in the direction of travel of the neutron, and a spin state s. And after the scattering, the neutron has gone to a wave vector of k primed and a spin state of k primed. So let's think about magnetic scattering to start with. In the case of magnetic scattering, what Professor Braham told you was that the potential that you need to plug into this matrix element is this thing here, Vm of Q, which has this, again, this magic factor in front here, which is the gyromagnetic ratio of the neutron times the classical radius of the electron over the Bohr twice the Bohr magneton. And then the thing that you see here is a dot product of the Pauli spin matrix, that's the one I introduced on the first view graph, dot producted with this thing here, which is denoted m perpendicular of q. What is m perpendicular of q? So the fact that it has a q here means that it's the Fourier transform of the magnetization in the crystal. So what I have is that if I have a magnetization density in the crystal as a function of the position in the crystal, and I take the Fourier transform of that just by multiplying it by e to the iq dot r and integrating it over r, that will give me a magnetization. So this is a vector, and this will give me a vector as a function of the wave vector q. What we know from the theory that you went through with Professor Braham is that only the magnetization components that are perpendicular to the q vector. So this means that the magnetization perpendicular to q, those are the only ones that cause scattering of neutrons. And this results from the dipolar nature of the interaction between the neutron magnetic moment and the B field within the sample, which is what it interacts with. So this operator here, let's get back to view graphs again. Not quite trivial. So this operator here, the m perpendicular of q, is what appears in the potential, the interaction potential of the neutron with magnetization in a crystal. So I can write this simply as in component form here, where this C here can either be an X, a Y, or a Z, and I sum over each one of these things to produce the total interaction potential between the magnetic interaction potential between the neutron and the sample. So now what I'm going to want to do is I'm going to want to evaluate this matrix element down the bottom here. And so what you can see is that if I take the Z component from up here, I will have the M perpendicular, the Z component, times the Pauli matrix, which has the Z component. And if you remember, this is a diagonal matrix with 1s on the diagonal. And since it's got 1s on the diagonal, it's not going to change the spin state because whatever the spin state is. And so if the spin state starts as being in the up state, this Pauli matrix multiplied by a spin in the up state is going to leave it in the up state. So this term, the one which has a Z on the M perpendicular here, is going to leave the neutron in the state which it started out in. Remember that the down state has an eigen value which is negative, so if I come in with a down neutron, I'm going to stay as a down neutron, providing I stick a minus sign in front of this thing. Now, this piece here is probably something that you have done in your quantum mechanics courses. If you look at an operator, let's look at this for a second here. Supposing you look at an operator like Sx plus Isy, and you look at what that does to one of these spin states. What you can easily convince yourself of is that if you take a 0-1 state, it's going to go to a 1-0 state. So that operator converts a 0-1 state to a 1-0 state. If you apply it to a 1-0 state, you get 0. And so this thing, and then if I do the same thing with Sx minus Sy, what you're going to find is that applying that to a 0-1 state gives you 0, and if you apply it to a 1-0 state, you'll get 0-1. So these things are what we call ladder operators. This one is what's called an up ladder operator. It takes the down spin state and makes it into an up spin state. If you apply it to an already up spin state, there isn't another state above it, so it gives you naught. This is a down ladder operator. It takes the up state, this is an up state, and makes it into a down state. If you apply it to the down state, it gives you 0 because there isn't a state below that. Matrices in here, which is what I just did on the blackboard. This combination of magnetization operators is going to cause a spin flip from up to down, and this combination of operators is going to cause a neutron to flip from a down to an up state. So what you can see is that depending upon which component of the magnetization you're talking about in a system, whether it's the component parallel to Z. Now Z, remember, is going to be defined by a magnetic field. So whether you're talking about magnetization component of this M perpendicular, which is parallel to some applied magnetic field or perpendicular to it, you will have different behaviors of the neutron spin when it's scattered. So there's another place where the neutron spin state can be changed. So it can be changed by magnetic scattering that you just seen, provided the magnetization that's causing the scattering is perpendicular to an implied field. But there's another situation in which neutrons are scattered, of course, and that's if they interact with nuclei. And you've been through this before, and what you found is that you can define something which is a scattering length, which this is the scattering length for the ith atom in a sample. This scattering length here depends both on what isotope of the nucleus you have. So it's different, for example, for deuterium and hydrogen. And it also depends upon the relative spins of the neutron and the nucleus. So you may have been through this before, but it's perhaps useful to go through it again. If we just define this scattering length BI is equal to its average value within the sample plus some small increment, which depends upon the site I in the crystal that we're dealing with, then of course the average of this thing, the delta BI over the sample, is going to vanish. So remember that what I need to do to find the cross-section is I need to find a product of these scattering lengths for the I site and the B site. And if I simply plug in this expression for BI, then I'm going to get a B average squared from each one of these two. I'm going to get a B average times this thing for the I site and this thing for the jth site, and then I'm going to get a product of delta BI times delta BJ. We know that these things average to 0. So when I look at the average of this whole thing over the crystal, this term, this middle term here, is going to vanish. This term will also vanish in general unless I and j are equal to each other, in which case I can't just simply take the average value of this times the average value of this, because they're the same thing. So this whole product here, delta BI times delta BJ, vanishes unless I equals j, and if that is the case, then I have to evaluate what the average of this, and the average of the squared deviation is the deviation itself. In other words, the value of BI minus its average, and then expectation value of that squared, and that comes out to be this thing here. So when you finally write down the scattering cross-section, you're going to have a piece from here, which is just the average scattering length, and that's going to have this factor that you're used to, the e to the iq ri minus rj, and then you're going to have this piece here where the ri and the rj are the same, so the phase factor goes out, and you've just got this quantity here multiplied by the number of atoms in the sample. So this thing is called incoherent scattering, and this thing is called coherent scattering. The incoherent scattering can arise from two different sources. As I said right at the top of this view graph, it can arise because you have different nuclear isotopes. So if you have different isotopes of an element, let's say nickel or iron in a sample, then the different isotopes will scatter differently, and so they'll have different values of this of B, and you'll have an incoherent scattering that results from that. You can also have an incoherent scattering that results from the fact that all of the nuclei have different spins. So let's think a little bit about that. Supposing you have a single isotope, so stick to having a single isotope in this case, and let's imagine that it has some spin quantum number I. Then if I have a nucleus and a neutron interacting with each other and forming some sort of compound state, then that state can either have a total spin of I plus a half, or it can have a total spin of I minus a half. Now you know what the number of states with a particular spin are. You just take twice the value of the spin and you add 1. So here we have twice the value of the spin plus 1, which just gives us 2i plus 2. The number of states that have this minus sign in them, I minus a half, is just 2 times the value of the spin plus 1. That gives you 2i. If the nuclei are unpolarized, then there's no reason to have anything other than equidistribution of the spins. And so each one of these combined spin states, the plus state and the minus state, have the same a priori probability. And if that's the case, the frequency of occurrence of the plus state is just the number of times the plus state can occur, 2i plus 2, divided by the total number of states that you have, which is the sum of these two. And similarly, the frequency of occurrence of the minus state is just 2i over 4i plus 2. You can then work out, of course, just what the average value of B is. It's this frequency of the plus state times B plus the frequency of the minus state times B minus, and if you just do the arithmetic there, you'll find that it has this thing. It comes out to be this value. Similarly, the average value of B squared comes out to have this value. So now we need to think a bit about what the nuclear scattering process is, and the simplest way, or that we can write this scattering length operator here, and that is dependent on the spin of both the nucleus and the spin of the neutron, is this linear form here, where you have a constant plus something which depends only on the relative orientations of the spin of the neutron and the spin of the nucleus. If you go back through what I did on the last view graph, and if you can look on Squire's page 173. Actually, if you go to, I think it's Amazon, and if you haven't got Squire's book, I think it's if you go to Amazon and you say, look inside this book, there I found that page 173 is there. Page 174 isn't, but page 174 doesn't contain anything useful. And all of the derivation of this stuff is on page 175. So if you want to see how, if you can't do this for yourself, it gets a little tricky. Then you can go on Amazon and see how it's done. But what you find then eventually is that this A is, and here it is what I had on the last view graph as the average of B. And then this B here is essentially proportional to the incoherent scattering length that I defined on the previous two view graphs. So what we've done here is we've split up the operator, which is the scattering length operator, into a part which is the coherent scattering, and a part which is the incoherent scattering that depends upon the spin of the nucleus. Now the isotopic spin incoherent part, that is the piece which just depends upon whether you have different isotopes, is actually not dependent on this spin, and so is actually in here, if you think about it. In other words, if there are different isotopes, then the different isotopes will have different values of this thing, and that will give rise to incoherent scattering, just as I said here. In other words, if you have different isotopes, there's an average value for all the isotopes of the nucleus, depending upon their relative abundance, and then there's a bit here which depends upon which isotope you're talking about, and that all is going to appear in this piece here. So now we can go back and we can work out what the matrix element is for the nuclear scattering, and of course we'll have our Pauli matrix in here, and since it's a dot product with the spin of the nucleus, there'll be a sigma x times an ix, a sigma y times iy, and a sigma z times iz. So if we look at the z term, again, because the iz term is multiplying a Pauli matrix, which is sigma z, and the sigma z is a diagonal matrix, we'll see that the neutron is not flipped by this combination. It's not flipped by this combination either. On the other hand, if we look back at these ladder operators that I was talking about earlier, if you have this combination of nuclear spins, ix, big Ix minus little the root of -1 times Iy, then you do get spin flip. So what have I told you there? What I've told you is that some part of the nuclear spin incoherent scattering is non-spin flip, and some part of the nuclear spin incoherent scattering is spin flip. The coherent scattering is always non-spin flip, because this is the A piece. Similarly, the isotopic incoherence, which comes in this piece here, is also non-spin flip. So now we can pull it all together and see what the various pieces are. So if the neutron is not flipped during the scattering process, then this is a coherent scattering plus isotopic incoherent scattering. Here's the component of magnetization which doesn't flip the spin, and here's the piece of the spin incoherent scattering that doesn't flip the spin. And similarly, non-spin flip down to down is all the same, except there's a minus sign here. The spin flip scattering up to down is very similar between the magnetization, the scattering due to magnetization, and the scattering due to the spin incoherent scattering. It has this form of an x operator minus square root of -1 times a y operator, and it's the same here as it is here. And then in this bottom one, which is the down to the up, you can see it also has that same structure. So those are the parts of the neutron scattering cross-section that you've already learned about, which contribute to these different spin-dependent neutron scattering cross-sections. So here are a bunch of general rules. And if you get anything out of this lecture at all, I would suggest that this is the most important view graph for you to try to commit to memory, because with this view graph, you can read all the papers on polarized neutron scattering and figure out what is going on. So the first statement is that neutron scattering, and this is something that you already knew from Professor Bohrholm's lectures, neutron scattering is only sensitive to the Fourier components of sample magnetization that are perpendicular to the scattering vector Q. And we call this thing M perpendicular, sometimes with the perpendicular sign, and here I've just written it out. So the corollary of this is if the sample magnetization is along Q, you can't see it with neutrons. Right? Because the component of the magnetization perpendicular to Q will then be 0, and the scattering is only sensitive to the component perpendicular to Q, and so we'll see 0 magnetic scattering if the sample magnetization is along the scattering vector. So the next piece is that the components of this vector, which are parallel to an applied magnetic field, that means parallel to the z direction, cause no change in the neutron spin state. If the neutron spin state comes in up, it goes out up. Comes in down, it goes out down. So the components of M perpendicular parallel to the applied magnetic field cause non-spin flip scattering. Similarly, components of the perpendicular magnetization that are perpendicular to the applied magnetic field. So you've got to you've got to draw yourself a picture, right? If, in this case, you've got to draw yourself a picture in which you have some axes here. And you generally are going to have, and then this is going to be the direction in which you apply your magnetic field. And so you are only going to be sensitive to magnetizations that lie in the XY plane. So only magnetization is going to be, in the XY plane is going to cause, excuse me, let me back that up. So let me put Q in here. That's what I was trying to do. If I put Q in here, where Q is in the XY plane, then only components of the magnetization which are perpendicular to Q are going to cause scattering. So that's somewhere in some plane that is perpendicular to Q. And then you've got to look and see which one of these components is parallel to, so M perpendicular along Z, and this one will give you non-spin flip. Whatever component of this is along X, so this is M perpendicular along X, that will give you spin flip. I probably said this wrong. This should be non-spin flip. And then the component of M perpendicular along Y will give you also spin flip. So you've got to figure out where the various axes are in your system in order to figure out whether you're going to have spin flip or the scattering due to magnetization in the sample, which one causes spin flip and which doesn't. Both coherent and isotopic incoherent scattering cause non-spin flip scattering, and the nuclear spin incoherent scattering is 2/3 spin flip and 1/3 non-spin flip, whatever the direction of the applied field. Now, if that wasn't obvious to you from this thing here, then you should probably go away and think about that a bit. Basically, if you have unpolarized nuclei, then each one of these, the Z, the Y, and the X, are sort of essentially of equal magnitude. And so, since there are two of them that apply to spin flip, and only one of them applies to non-spin flip, that's where you get this factor of 2/3 and 1/3 from. Okay, Colin, do you have to leave probably? Yeah. Okay. So so now we've talked about what happens in these in the scattering experiments. Now I'm going to talk a bit more about polarized neutrons themselves. So the practical ability to do these experiments really depends upon your ability to be able to control the neutron polarization state. So the first thing to know is that once you have a neutron that's polarized in a magnetic field, as long as you don't turn the field off, the neutron is going to stay polarized. If the magnetic field changes, then the polarization state of the beam, this vector P, is going to obey this vector equation here, where this gamma L is called the gyromagnetic ratio of the neutron. It's the ratio of its magnetic moment to its spin. So what you find if you solve this equation is that if you put a spin in a constant magnetic field, so here down in this picture here, I'm imagining that somehow or other I suddenly I have a beam polarization, this vector P, that is at some angle to a applied magnetic field. That's kind of a Gedanken experiment. It's hard to actually do, but maybe you can do it. I'll actually show you a way that you could do it. But if you suddenly have a polarization vector which is at an angle to a magnetic field, what's going to happen is that these solutions over here are the ones that are going to apply. You can see that the Z component of the polarization, that is to say the one parallel to the field, isn't going to change just because of this cross product here. The component, the PZ, since B is along Z, the component of P along Z is going to give you 0 contribution to this cross product. So the Z component of the polarization is independent of time. The other two components change in this sinusoidal manner, which essentially describes a rotation of this polarization vector around the applied magnetic field. So this is called precession, and it's just like what you would see with a, see you later, Colin. It's just like what you would see with a top. If you spun a top on a table and pushed the spinning axis off a bit, you'll see that it precesses around the vertical direction. So this is what happens if you suddenly put a polarized beam, polarized in some direction, in a magnetic field. It precesses around the magnetic field direction. Well, that's normally not what happens. What happens is that you've got a beam whose polarization is lined up with a magnetic field. And what's going to happen is that somehow or other the magnetic field is going to change its direction relative to the polarization direction that you've defined. So, for example, if you have a field here and your polarization is lined up with it, and then you start to rotate the field, what's going to happen to the neutron polarization? Well, this is a little diagram that was first invented by Otto Schurpf to try to show what will happen. So what you need to imagine here is that this outer circle here is the globe. It's the Earth. And this circle here represents the equatorial plane of the globe. And at some point, the neutron spin is lying on this plane, the equatorial plane, lined up with a magnetic field, so that the start value of the spin is S0 and the start value of the magnetic field is H0. Now what you're going to do is you're going to move the H round here in the equatorial plane of the globe. So H is going to move from H0 to H1 to H2 to H3 to H4. And you're going to ask, what does the spin do? Well, if you imagine an ice cream cone, which is lying on this equatorial plane, and the line where the ice cream cone lies on the equatorial plane, imagine drawing the spin along that line, and then unrolling the cone on the equatorial plane, and the drawing of the line of the spin on the ice cream cone will map out a trajectory like this, the end point of the vector, as that cone unrolls on the equatorial plane of the Earth. And that's what the spin does as you try to move this magnetic field around. There are a number of different cases that you can imagine here. One obvious case is where you do this slowly, and the other case is where you do it very fast. The slow case is where you would just rotate it around here. The fast case is where you'd suddenly switch it from here to here in a very small amount of time. What one needs to draw is a diagram that looks like this, in which this omega L, one of the things that I did not point out properly on the previous view graph is that the speed of precession of the polarization around the B field is the rate of rotation is this thing called omega L, which is called the Larmor frequency. It's a number in radians per second, which is proportional to the magnitude of the field. So if you draw this triangle here, this drawing here, where this length is the magnitude of the rotation frequency of the precession of the neutron. It's the Larmor precession frequency. And this horizontal direction here represents the rate of rotation of the magnetic field. So it's the rate at which the angle of the magnetic field changes. Then obviously this slow rotation case, or not obviously, but it turns out that this slow rotation case is the case where omega is very much smaller than omega L, so this angle delta here is very small. This delta here is the opening angle of this ice cream cone. So here's the ice cream cone here, is so the delta, or actually it's the half opening angle of this ice cream cone. So when the rotation rate is very small compared to the Larmor precession rate, this ice cream cone has a very small piece of ice cream in it, and has a very small opening angle. And as it unrolls on this plane here, the spin stays pretty much in contact with where the magnetic field is. And so in this case, where the rate of rotation is small compared to the Larmor precession frequency, effectively the spin follows the direction of the magnetic field. It precesses about it a bit, but basically it follows it. And that's the situation we're going to be in if we try to guide the polarization of the neutron beam through the instrument. On the other hand, if this rotation of the speed of the field, goes suddenly from here to here, in other words, this vector here is much bigger than the vector representing the Larmor precession rate, then this opening angle, there's a huge piece of ice cream in here, this has a huge opening angle, and then the spin neutron polarization can't follow the rotation of the field at all, and in certain cases, as you'll see in a minute, it'll just completely ignore it because it happens so fast. So we need to think about this ratio of the Larmor precession frequency divided by the rate at which we're changing the angle of the magnetic field. And that thing is called, in the jargon of the field, the adiabaticity parameter. And the higher the adiabaticity parameter, the better off, the better the neutron spin can follow the magnetic field that's changing. So in order to work this out, we need to know some numbers. And this table gives you essentially all you need to know. The one that I always remember is that let's come back to that. So supposing I apply a field of 10 Gauss, that's a very low field. If I apply a field of 10 Gauss, the Larmor precession frequency is 183,000 radians per second. So that's the rate of precession of the polarization around the field. The number of precessions per millisecond is about 29. And if you have a 4 angstrom neutron, which is going at about 1,000 meters a second, so it'll take about a millisecond to go 1 meter, then, of course, the precession will go through the number of turns here in number per millisecond. It's roughly 29. The number I always remember is 30 Gauss centimeters per turn for a 4 angstrom neutron. So 30 being roughly equal to 29. So the number, so when I'm working on a polarized beam, that's the number I always try to remember, is that 30, if a 4 angstrom neutron goes through 30 Gauss over a centimeter, or a Gauss over 30 centimeters, doesn't matter which, it will turn through, the spin will precess through 1 turn. Provided this adiabaticity parameter is large, as I said, you can guide the spin of a neutron. And the spin of the neutron will, I shouldn't say neutron spin, I should say neutron polarization. I told you at the beginning that you couldn't apply this to a single spin, but we tend to be lax in our language, and you'll hear people say the neutron spin. I say it half the time too, but in what this should say is that the neutron polarization will adiabatically follow the magnetic field as it varies along the neutron trajectory. And the sort of magnitude of the guide fields that you'll need to make sure this happens depend upon how fast the neutron is going, of course, because that's what determines how fast the angle of the field is changing in the frame of the neutron. So if the neutron is going very fast, which would be the case with a 0.4 angstrom neutron, then the direction of the field is changing very fast, and then you need to make the Larmor frequency very large in order to guide the neutron. So that's a 250 Gauss field. When you get up to a 10 angstrom neutron, you can do the thing in 5 or 10 Gauss, and the neutron will follow the field quite easily. So here's a picture that sort of tells you what's going on. If you want to guide the polarization of a neutron beam, and we'll see why we need to do that in a few slides, but if you want to guide the polarization of a neutron beam, you can start it off in a parallel, defining the quantization direction here with a magnetic field, and then you can just gradually rotate the field around to some value which is direction which is perpendicular to the initial direction, and the spin will have changed with it. What's this distance? Usually, on most neutron scattering instruments, you can do this over 5 to 10 centimeters. So if you have the right magnitude of guide field, the sorts of magnitudes that you see in this table at the bottom here, and you simply take one guide field with its field vertical and another guide field with its field horizontal, let's say 10 centimeters apart, then the neutron will happily follow the field that's the overlap field between the two guide fields. In other words, it will follow this change in the direction of the magnetic field between the two guide fields. It's quite easy to by the way, one of the things that you have to have with you when you're doing polarized neutrons, well, there are two things you have to have with you when you're doing polarized neutrons. One is a Boy Scout compass, because you want to know which direction a magnetic field is pointing in. You'll be amazed at the number of times when you think the magnetic field is pointing upwards when you've actually got one of the guide fields on upside down, and that will cause depolarization of a neutron beam. So you need a little compass to tell you which direction the magnetic field is in, and then you need a Hall probe to tell you what the magnitude is, because you're going to want to know whether you've got a large enough guide field, whether the Larmor precession frequency is large enough, and as I told you, the Larmor precession frequency is just proportional to the magnetic field. So the bigger the magnetic field you have, the larger the Larmor precession frequency, and the faster you can afford to rotate the magnetic field and have the neutron follow it. If the guide field direction changes suddenly, then, which meaning that the adiabaticity parameter tends to 0, then the neutron polarization doesn't have time to change. So here's a situation in which you have a magnetic field H0 pointing upwards, and then suddenly you change the direction of the field so that it's pointing downwards. Yes, it does. So what happens in this case, the nomenclature is a bit strange, but if you have a magnetic field pointing upwards in the plane of the view graph, and then another one suddenly pointing downwards, the neutron spin does not have time to precess. And so basically it goes into the new field in the same direction as it started out. But now you'll see that the direction of the polarization is opposite to the direction of the magnetic field. So now the polarization is minus whatever it was over here. So if the polarization starts out as 1 here, in other words, all of the neutron spins are aligned with the magnetic field, if you make this sudden change of magnetic field from up to down, then the neutrons will stay polarized, but now they'll have a polarization of -1. I see what this is now. This is the y direction in this plot, and so this is field at h equals y equals 0, and then this down arrow here is the field at h equals y equals 0 plus a little bit. So this would allow you, if you wanted to make what's called a flipper. In other words, a device which switches the direction of the polarization with respect to the magnetic field. So, as I said, in order to maintain the neutron polarization, you need a guide field, or you need strictly zero field. If you have strictly zero field, and I mean strictly zero, which is very hard to achieve, the neutron spin state won't change. But if you're not willing to try to achieve zero field, then what you need is an applied field which will change, which will maintain the direction of the polarization of the neutron beam. It's quite easy, by the way, in these cases, as I said, to screw up and get things messed up so that you depolarize the beam. The easy way is to flip the direction of the guide field, in which case you will depolarize the beam. And the reason is, if you have a guide field here which is up and a guide field here that is down, halfway between you have zero field. There, the zero field, the Lamour precession frequency rate is 0, but the field rate of change is going from up to down, and because it hasn't happened suddenly, the neutron will feel that, and it will get completely depolarized, or the beam will get completely depolarized. So as I say here, a compass and a hole probe are the indispensable tools for checking this. So you have to make sure that the field direction is not varying too quickly, and that the field in the region where you're interested is not too small, so that you've got enough, big enough Lamour precession frequency. So what you'll see as we go through the experiments is that one of the essential devices that you need to have to do these experiments is something called a pi flipper. And the reason for that is that you want to be able to easily exchange between one spin state of the neutron and the other. You have to do that, of course, if you want to be able to bring a neutron spin into a sample either in the upper or down state. Because if you have a device that produces polarized neutrons, it will always produce polarized neutrons in a particular direction relative to a magnetic field. And unless you can change that, you're always going to have the neutrons coming into the sample in the up state. So if you want to measure the scattering cross-section, let's say with neutrons coming in a down state, you've got to be able to flip the neutron spin. And the devices which change the neutron spin state or the polarization from, let's say, predominantly up to down are called pi flippers, and they also change it from down to up. So here's the simplest one of that type of device. And that's just simply a current sheet on the left here, and you can see that the way this is done is that you've got current. So you have a piece of wire that brings a current down through here. It goes over to here, it comes back, it goes round, goes down here, and makes a figure of 8. And then you spread out the wires in the middle here so that you have essentially a bunch of wires all with the current going in the same direction. In that case, the field on one side of the wires is a magnetic field on one side of the wires, let's say the side nearest us, out of the plane of the screen, is in one direction, and the field on the other side of this screen is in the opposite direction. So now you've got a magnetic field that changes from, let's say, going from left to going from right to left to going from left to right in the thickness of a piece of wire, and that's fast enough for the neutron to ignore it, and that will flip the polarization of the neutron from one direction to the other direction. Here's a similar thing in which one could have, let's say, a Meissner shield, a superconducting shield, with a field on the outside and a field on the other side, which is in whatever direction you want, but let's say it's in the opposite direction, in which case that will cause the neutron spin to flip, because now instead of the spin and the field being aligned as they are outside, they will be anti-aligned inside. Here's another one, which is perhaps what we'll finish with this time, and that is a device which is called a Mersenne flipper, which relies on a DC current in order to flip the neutron. So you can see that if you had a neutron spin, which is horizontal here, so this means S initial, and if you suddenly managed to apply a field in this direction, what would happen is that the spin would precess around this B field, and if you managed to not apply the field or take the field off when the spin got to this point, then you would have rotated it through 90 degrees. So that would be called actually a pi/2 flip. If you have the field perpendicular, if you suddenly apply a field perpendicular to this initial spin, then what will happen is that the polarization will precess around the magnetization, and if you can remove the field at the time when the polarization gets to this point here, you will have flipped the spin. So let's just concentrate on the pi flipper. If you make yourself a solenoid, a flat solenoid, so this is a coil of rectangular cross section. In other words, if you look down on this coil, it will have a rectangular cross section. The current is flowing around it like this, so the B field is upwards. If it's long enough, there's no field outside here because these ends are far enough away. And so now if I have a neutron whose polarization is, let's say, horizontal, it comes along here, it enters this solenoid, suddenly sees a field in the vertical direction, starts to precess around the field, and if I choose the current in the coil, in this coil correctly, what will happen is that I can tune it so that the neutron will have its spin pointing in the opposite direction when it gets to this end. And that turns out to be very easy to do. Here's a picture of a device which goes into a guide field. So down here on the lower right, the top, this piece here is made of iron. The bottom piece is made of iron. And then between the two are bar magnets. So this piece here is a bar magnet. There's a bar magnet over here, and there's a bar magnet in each corner. So now what I have, this is a guide field. Between this top iron plate and this bottom iron plate is a vertical magnetic field. Now let's supposing I wrap two coils as shown in this top diagram here. And I insert this device in here. Just so this device here is this pair of coils. This coil here, the one that my pointer's on now, produces a vertical field. I can organize the current in that so that the vertical field that's produced by that solenoid exactly cancels whatever the guide field is. And then I can apply a current through this coil here, which gives a horizontal field. And if I make sure that the current is correct or the field is correct, what's going to happen is that the neutrons are going to come in, polarized vertically in this guide field, and they're suddenly going to see a horizontal field. They're going to precess around that field, and if I organize the current correctly, they will be flipped. And here's the number of turns that I will get of the polarization as a function of the field inside this coil, its thickness, and the wavelength of the neutron beam. So I think with that, I'm going to stop there, and I don't know whether people in various sites can ask questions or not. So do we have questions?
Yet.
Yeah, no questions yet. So feel free to ask questions if you want to. Somebody's typing. Colin is. What is that?
Okay. Great lecture. Thanks.
Okay. All right. Then we'll come back to polarized neutrons again on Thursday.